times the mass times Vf squared minus Vi squared.
And what happened to the ions, or to the
Remember, these are all scalar products, so
Oh, right, okay, so.
the
Is
vector
that
just
a-
dropped away.
Is that a negative sign or is that an equal sign in front of the 1/2? You just
That's an equal sign.
Okay.
We have derived work total.
Yes, but we're gonna take it farther. Because I'm gonna distribute the 1/2 mass here. So I get equals 1/2 mv final squared minus 1/2 mv initial squared. Ooh. If you had physics before, you know what this is leading to. Now 1/2 mv squared shows up twice here, so physicists said, you know what? I don't feel like writing that, I'm just gonna come up with a letter to represent 1/2 mv squared. So what I'm gonna do is I'm just gonna let capital K be 1/2 mv squared. And that brings us to my total work is equal to K final minus K initial, which means my total work is equal to the change in K. There we go. Simpler looking formula, as promised. And you're all looking at it going, wow, that's incredible.
Does K come from Kepler or is
No, K does not come from Kepler. It does come from something though. It was not just a random letter I picked.
Where does it come from?
This 1/2 mv squared, this K equals 1/2 mv squared, that K stands for kinetic energy. Connecting back to the E word was used earlier, K equals kinetic energy. And now the part to delight everyone in here. And make those who are not here, watching it on video, feel sad, because they were not here for this. When you're working on your Nobel Prize winning dissertation, and you're trying to figure out the formula for kinetic energy, right there. Almost every other pretty much any other formula we use, there's a small tweak to it as we go. But not here. 1/2 mv squared.
That by voice.
30 years from now, sure, I'm alive still then. 30 years from now, we're gonna run into each other. We're gonna try to remember how we know each other. And then I should be able to ask you, what's the formula for kinetic energy? And you should be able to reply, 1/2 mv squared. I believe the video associated with this is the formula you need to know. Might even be the formula you need to know cold. So what I'm gonna do is I'm gonna ask you what's the formula for kinetic energy, and all of you, and I am serious, all of you in unison will respond 1/2 mv squared. Here we go. What's the formula for kinetic energy?
1/2 mv squared.
The chorus of angels I was hoping for. Now, this is kinetic energy. Kinetic from the Greek word for movement, as in kinesiology and kinetics and kinematics. This is the energy associated with motion, which makes some sense because we have the speed in it, and that is speed, not velocity. But physicists love conservation laws. They thought, all right, so I've got this kinetic energy. It seems like we should make up another energy. And of course they did. It is potential energy. Let's get rid of any questions on this before I erase it?
You see what you're saying now? You can't have chemistry without physics. Because now I could go to my chemistry teacher and tell her, I know where you get K from.
It's the chemistry, the central science, you know, like the middle child, and all the problems associated with that. Unlike physics, which is kind of like, I would say the youngest child. You know, parents stop when they hit perfection. You know, that's, who agrees with me? We have no youngest children in here? All right, we got three of us against them. All right, anyway, so they came up with this idea of potential energy, the potential to do work, which I always found an incredibly useless definition. Now the symbol for potential energy, capital U. I think it's from the German. Some textbooks will use PE, but that's too much writing for it. Now, if I ask you what is the formula for potential energy, the proper response is, which one? What's the formula for potential energy?
Which one time?
The one associated with whatever conservative force is involved. So to understand potential energy, we need to talk about conservative forces. And non-conservative. Their imaginations were on fire that day when they came up with that one. Now there's a formal definition to conservative forces, however, it's probably easiest not to do the formal definition of a conservative force and instead just give you the list of all the conservative forces we have covered so far. Done. That is the only conservative force we have dealt with up to here. Now, we will soon get into an elastic force. That is also a conservative force. That's pretty much it for this course. In 152, there's electric and magnetic. And that's pretty much the conservative forces for 151 and 152. The classic non-conservative force, friction. Friction, normal force, non-conservative. So these are examples of conservative forces. Now, why is it called conservative? And hint, it has nothing to do with politics.
Because it has to do with saving energy.
Close. Saving is probably, no, I guess that could work. Conserving energy. Conservative forces conserve energy. Now in physics, conserving energy means that you don't lose any. Whatever you start with is what you end with. We can word it slightly differently, is that a conservative force will change energy from one form to another. Non-conservative force will transfer energy from one object to another. So if I push this notebook across the table, I did non-conservative work on it because I transferred energy into the notebook. If I take this marker and I drop it, the only force acting on it was the force due to gravity. As it gained kinetic energy, it lost potential energy. So the energy transformed from one form to another until it hit the floor. All right, a couple last thoughts here before I guess we'll see you for a week and a half.
What will I ever do?
I know. Just try to comfort yourself as you're crying yourself to sleep. That physics will return, and you can always study physics on your own. This is known as the work energy formula. Sorry, work energy theorem. Now, frankly, I don't think it's a theorem. I think it's the work energy definition, but they didn't consult me.
Out there.
Work, if I have non-conservative work, energy is not conserved, so non-conservative work is gonna be equal to the change in energy, where E is equal to kinetic plus potential. And the conservative work is equal to the negative change in potential energy. These three equations together are the work energy relationships. So I know there's at least one master set problem, which is basically an exploration of this. But, and I guess with one last thought, because I asked about the potential energy and in response, if I asked you what's the formula, you were supposed to say which one, because every conservative force has a potential energy formula. So if the force and potential energy, so if we're talking about mg, weight, mg, the formula is mgh, plus a constant. If the force is the generalized, big G, mass 1, mass 2 over r squared, negative G, mass 1, mass 2 over r, plus a constant. The electric force, oh, that's the gravitational force. The elastic force, the force is negative K delta x, that's a lowercase k delta x. This is 1/2 lowercase k delta x squared. The electric force we'll deal with next semester for those who are with us. Hopefully all of you.
Next quarter. Or
Next semester.
B semester.
No, 152.
Oh, okay, next semester.
Yeah.
Yes. And, you only teach the 8 AM classes, right?
I was just sent a proposal for my schedule for the spring, and I've not looked at it more closely, but I think I assume there's a 152 offered in the same time slot as this is. But yeah, I believe I will be teaching that.
Awesome sauce. Make sure I stick with
So you don't have to get used to someone else's sense of humor.
it. Yeah. Bit by bit, I'm understanding Fox talk.
Good.
What did the fox say?
It was such a delight having the last name of Fox when that song was hit. I think on that note, sort of thinking of a cliffhanger because I skipped over some derivations. But when we come back, we're gonna start off with, what was the last thing I did? Let's see, so I don't have when the next test is.
Test 1B.
Test 1B.
We wrote that down.
Yeah,
Um,
October 25th.
Oh, there it is, yes, thank you.
yeah.
So 2 weeks from yesterday, 3 weeks from yesterday.
You bring